Now, there are a lot more ions than there are elements. There's a lot more ions in the world than there are elements because some of the ions are polyatomic. Prefix poly. What does poly mean? Many. So many atomic, many atoms. Polyatomic ions are groups of atoms that stick together and have a charge. So they act as a unit. A lot of them they actually thought were elements for a while, but eventually they could break those pieces up. So there are some groups of atoms that stick together as a unit, and in there they've lost 1, 2, or 3 electrons, or gained 1, 2, or 3 electrons. So there's some common examples. So phosphate, ATE at the end, okay, has a phosphorus and 4 oxygens hooked together, and somewhere in those 5 atoms it lost 3 electrons. We don't know where, but somewhere along the line it lost 3 electrons. So that's a group of atoms, and that travels together as a unit. It doesn't break up. So phosphates are good fertilizers. So when I was in high school, they were taking phosphates out of detergent because people would wash their clothes, the water would run into the lakes and streams, and phosphate was a great fertilizer. So the algae would bloom, get lots of algae growth, and then they'd have used up all the fertilizer, so all that algae would die. And when it died, it would start rotting and using up all the oxygen in the lake, and the whole lake would die. Okay, those phosphates were killing off streams. So phosphates. Okay? It's the P in ATP, right? It's the T in ATP. The thing that makes the bubbles in your soda is carbonation, which is carbonate ion. The stuff that makes vinegar is the acetate ion. So right now all I need you to know is they exist. That there's this group of atoms called carbonates when you put together 1 carbon and 3 oxygens. And when you do that process, you gain 2 extra electrons. There's 2 extra ones in there someplace. Acetate, we put together these 7 ions, 7 electrons, there's 7 atoms. Put the 7 together. And in the process of putting them together, I actually have to put in 1 negative. So the names often end in ate or ite. So if you got a package and you start reading it, and it starts saying things like ate or ite at the end, they're just talking about a polyatomic ion. This doesn't have anything in it. Wow, that's what I'd like to see. No additives. But ate or ite show up there. We'll talk more about polyatomic ions later. I just want to let you know that non-atoms are monoatomic, which is what we're talking about so far. This is one atom has a charge. That's monatomic versus polyatomic. Okay. So those kinds of ions we're going to have to deal with. We bring them together. They make ionic compounds. And what do ionic compounds behave like? That's what properties are. Words that you would use to describe them. What makes them different from other elements. Okay. So one of the features of ionic compounds is they have a crystalline structure. Okay. That means they're crystals. A regular repeating arrangement of the ions. There's going to be a pattern that puts them together best. Okay? So So if I got sodium chloride, sodium's got a positive charge, I know it's going to be next to it is not another sodium. It's got to be a negative charge, right? And then next to that chloride is going to have to be another sodium. But I have a chloride and a sodium and a chloride. Can you see why you'd want to do a repeating pattern of this when it's just opposite attract? We don't want to put two chlorides together because they'd push apart. We want them to stick to each other. We don't want to put two sodiums together because they'll push apart. We want them to stick to each other. So I need to get the negative pieces in between the positive pieces and the positive pieces in between the negative pieces. And there's going to be some pattern that makes that work. Okay? The ions are strongly bonded. An ionic bond is strong. It's hard to break. Not only is it hard to break, it's hard to bend. It's rigid. It's unchanging. And because that bond is strong, that they're holding them together, they're going to have high melting points. Okay? To melt them, I'd have to take the sodium and the chlorine away from each other, break that bond, and that's going to be really hard to do. So when we say they have high melting points, salt, sodium chloride. Have you ever seen salt melt? No, you've seen it dissolve a lot, but have you ever seen it melt? No. Because if you put some salt in your pan and wanted to heat up the pan to melt it, it would be a race between which would melt first, the salt or the pan. That's what we mean by high melting points. There are a few that have lower ones, but in general, they're very high. Okay. So ionic compounds always have these properties. I want to show you what the crystalline structure looks like. So this is what a crystal, how the atoms are arranged in a crystal of sodium chloride. So that means this is made up of sodium atoms and chloride atoms. Sodium makes a 1 plus, chlorine makes a 1 minus. You look at that? One of these colors is sodium and one's chlorine. Which one's which? Okay, so you say purple sodium and yellow chlorine. Was that what you're going to agree with? And he thought the opposite. So the only clue we have is size, right? Okay, so you're tempted to say, oh, they're on the same energy level. So as I go across, they get smaller. And chlorine is smaller than sodium. Except I don't have sodium and chlorine. I've got sodium after it lost an electron. So the sodium looks like neon, only smaller. The chlorine looks like argon, only bigger. That makes sense? So the purples have to be the chlorine, and the yellows have to be the sodium. Can you see that it alternates? So this is the face. It alternates on the face, right? And then right behind it is another layer that alternates exactly the opposite way. And then there's a layer that's just like the first layer. And notice how, what kind of shape does that look like it draws? A square in every direction, right? So it looks like it draws a cube, doesn't it? Okay. Well, let's find out. Say, what do you mean, let's find out? Okay. Over here, I've got my microscope, and I've got some salt, and a slide. I just need a few little pieces there so we can see it. Come on. Don't freeze on me. It looks like it froze on me. Did it freeze on me, camera? Camera. Well, the easy way to tell would be to turn this off. Yeah, it froze. So I spent all morning setting it up, and then it freezes on my way out. So let's look and see what I can do with this. See if I can get it to work for me. Let's try it again. All right. See? For some reason, it decides that I want it side by side, and I didn't do anything. I walked across the room. And so let's see if it's still frozen. It's gonna work on this. Let's do it the quick, easy way. Okay, all right, it's working. That's what we like. So let's look and see what these grains look like. Okay, lowest power. What shape would you say those are in general? Cubes. Do they have to make them into cubes? Did somebody cut all these into little tiny pieces? Exact opposite. They just let the water evaporate. And those ions had to come together. And when they come together, they make that pattern. Now you say, ooh, they're rounded. That's because they're in a thing and they've been beaten against each other for years and years. We make them fresh. It's pretty sharp cubes. And you can see that this grew as a cube and this was growing as a cube, and then they grew together on top of each other. So you can see that it was cubes that were growing. So salt always grows in cubes. So the crystal structure you see underlying it actually shows up with what you can see. Okay. Now, not all there's a bunch of different patterns, because you're not going to be able to do that with something that's got 2 NAs and 1 O. We're going to have a different pattern for that. There's about 7 different patterns they come into that make different ones. So that one is, let's turn this back on. Okay. So that is what salt does. It's nice little cubes. I don't have to do anything about it. They're all little cubes. All I had to do was open up the thing and pour it on. And this stuff makes a different shaped crystal. And the crystal it makes is kind of hard to make, so that we can actually let it grow in front of our eyes if I do my job right, and see what kind of crystal it grows into. And I said most things have really high melting points. I picked this ionic compound because it doesn't have a high melting point. I went out of my way to find something that had a low melting point so I could do this. Come on, get hot. I need you to get hot. Okay, when I want it hot, it's not hot. Oh, come on. Got to be able to do 2 things at the same time. Where'd it go? It was right here. Don't want to have to fake it. Guess I'm faking it. Come on. Get hot. Make a cloud of steam. That's what I get for turning off earlier. In 3, 2, 1. Get hot. No, don't turn off. Come on in, melt. There we go. I hear it boiling. So this will melt just below the temperature of boiling water, so I can use boiling water to melt it. Get it nice and melted. Okay. Okay, as it cools down, you can watch that crystal there in the corner. So is this the same shape crystal as sodium? No, it's not the same shape. But it grows at that angle. See how that long, narrow one is growing? So its angle is, it's got a long axis and a short axis with some angles built in. Okay? But those angles show up as you let it solidify. So, see if I can do it a second time without burning myself. I gotta get it all melted, and it doesn't want to melt without burning me. Now I got it too hot. I can't get my hand anywhere near it. Get it work a little better. Get a little hotter. Melt for me, melt for me, melt for me. Oh, come on. It's not, so it's stuck to my fingers. Is my liquid flowing? Yeah, I'm not going to be able to find it here. It's too messed up. Well, but you saw that they grow at different angles as well. Okay? So our crystalline structure is not always nice little cubes, but it's always a pattern. There's always some pattern that maximizes attraction and minimizes repulsion. Okay? Okay, we said one of the properties of metals was they conducted electricity. Okay. Conducting electricity is allowing charged pieces to move. You have to have charged pieces, and they have to move. Okay. So metals hold on to their electrons really weakly. So those electrons can move around in a metal. That's why metals conduct. But can ionic compounds conduct? Well, in a solid, they're locked in place. It has charged pieces, but they got to be in that pattern. Right? Whatever the pattern is, they've got to be in it. So they have charged pieces, but they can't move. Ionic solids are insulators. Okay? Fact is, if you look at the power lines, you'll see that there's a little piece of porcelain between the wire and the telephone pole. Porcelain is an ionic compound. It's made up of ionic compounds because we want an insulator between the wire and the pole, because we don't want to touch the telephone pole and have a shocking experience. Yeah? But remember, when we talked about melting, I said we have to take those ions and tear them apart, right? Well, if I'm tearing those ions apart, then they can move around. So going from solid to melted changes it from not being able to conduct to being able to conduct. So melted ionic compounds can conduct electricity. Why am I not going to show you that? What's the challenge in that one? They melt at a really high temperature. We're not going to build wires out of ionic compounds because it's kind of hard to keep the wires at 800 degrees Celsius. But that's not the only way to tear salt apart. Okay? There's another way to tear salt apart, and that is throw it in water. If I put salt in water, does the salt stay in one place? No, eventually it's spread all the way through the whole cup, right? Okay, so that means it's got ions that can move. So if I dissolve it, then it'll conduct. To show you that, first I have to give you the official warning. Kids, don't try this at home. Okay? So, here I got a light bulb. That light bulb is not on because it's not plugged in. I'm going to plug it in. If I can, find an open spot. Plug it in. The light bulb is still not on. And that's because the wire is broken between this pole and that pole. So the wire goes in, goes out. So it's not, light bulb's not on because the electricity can't get from here to here. Okay? So I'm going to help that along. Kids, do not try this at home. Nothing happened. Water's not ionic. Water doesn't conduct electricity. You say, well, then why do they warn us about it? Because you are full of dissolved ionic compounds. So while the water doesn't conduct electricity, we're not trying to protect the water from the electricity. The electricity doesn't want to go through the water. It wants to go through you. So if I put you in the water and add a little bit of that salt and let it dissolve, it conducts electricity. You have lots of salt in you. That's why you don't want to be in a bathtub with a toaster. Okay? Don't use the hairdryer in the bathtub. It ruins the toast. That's the real issue. You can't get crunchy toast in the bathtub. Yeah. That's because you've got insulators on your shoes. Okay? So as you brush up against things, you're rubbing electrons off or on. And because you've got insulated shoes, it can't go anywhere. So that extra charge stays with you until you go to something that it can jump to the ground. Because electricity wants to get to the ground. So it's on its way, and your shoes stop it. So you normally, we got solid, you have to have like rubber shoes. And sometimes you can do it simply by, you can rub the electrons off of carpet by dragging your feet. And they pile up on you, and then you can give them to your friend. We were all in 4th grade once, right? We all did that. And Southern California is great because the humidity in the air would carry that charge away so that it lasts for a while here. He said, so you put stuff in water, it conducts. Well, no, it's not just because I put stuff in, because the stuff I put in was ionic. Okay? Because if I do the same thing with, you notice that I'm not touching the poles, and don't have any metal anywhere near me. Okay? If I do the same thing with sugar, sugar dissolves in water, right? But the light doesn't come on. That's because sugar is not ionic. In fact, that's the test. If a chemist wants to know whether something is ionic or not, they try to dissolve it and see if it conducts. So if I've got some baking soda, okay, and I put a little baking soda in, I'm going to do it from a distance, not put this metal in there. Okay, and as that baking soda dissolves, the light bulb comes on. What does that tell you about baking soda? It's ionic. It's a pretty simple test, right? See if it conducts electricity when dissolved. Okay? So we can tell the baking soda is ionic. Okay? So water conducts electricity lousy, so it'd much rather go through you, and along the way, it stops your heart. That's the issue, is that the electrical signals mess up your heart. If your heart's electrical signals mess up, you die. Yeah. Nothing would happen until I go to pick up the knife. I mean, I've done this before. It's not, well, what's this? I can just do this. Right? If I touch metal to these, metals conduct, right? So just touch both metals. Nice wooden handle. Wood is not metal. Would help stop it because you're not going to make that contact. Depends on how much voltage you have, whether it would go through the glove or not. Okay, voltage is how hard the electrons are being pushed, and if you get high voltage, they'll push right through stuff. Okay, so everybody okay with the properties of ionic compounds? Okay. Ionic solids are brittle. Remember, brittle was the opposite of malleable. Right? Brittle was the opposite of malleable. Malleable means you hit it with a hammer and it bends. That's what metals do. There's metals in ionic compounds, but they don't bend. Let's say there's my regular repeating, my crystal arrangement, right? What would happen if I hit the top row with a hammer and try to push it that way? Well, as soon as I try to push it that way, the positive is going to be next to the positive, and the negative is going to be next to the negative. And they're not going to stay together anymore. So if you try to move just one atom over, it falls apart. You can't do any bending at all. There's no flexibility. They have to be in that line, or they don't fall apart. They get pushed apart. It's not that they're no longer attracted. You line up things that repel, and it gets pushed apart. Okay? So strong repulsion breaks apart that crystal. There we go. So you hit it with the hammer. You hit it with the hammer, and the negatives line up with the negatives, positive line up with the positive, get pushed apart, you've got shattered crystals. And so, where are we at? And so, that's what ionic compounds are like. Okay. So now we know about their properties. The next thing we need to know is how to name them. And I fight this because I know how to name them, and I fall myself into following the rules when you don't know them yet. Okay, so the names of ions. Okay. Well, cations keep the name of the metal. Whatever the name of the metal is, that's going to be the name of your cation. So here's this simple example. Calcium is Ca. Ca makes an ion. It makes a 2+ ion. Loses 2. So we call Ca2+ the calcium ion. So, which one do you need for healthy bones and teeth? Anybody want to eat calcium? You did that lab last week, right? You got to eat calcium? No, you're not going to eat calcium, are you? Okay, so what you want is calcium ion. Once it's given away those electrons, it's not nearly as dangerous. Right? For the anions, the negative ions, change the ending to IDE. That IDE is going to tell us that it lost electrons. Oh, sorry, gained electrons. It's got a negative charge. Okay. Oops. So I look up on the periodic table, I see chlorine. Chlorine's a nonmetal. It's going to gain an electron to look like a noble gas and get a 1 minus charge. When it's got that 1 minus charge, we can no longer call it chlorine. So we call it chloride ion. So the metals, you leave their name alone. The nonmetals, you change the ending. So that's how we're going to know which one we're talking about. So calcium ion, chloride ion. Okay, so what would you name the ion made out of magnesium? That would be magnesium ion. It really is that straightforward. How about the one made out of oxygen? Oxide. Okay. What about nitrogen? Take off the agen. Nitride. Just take out the whole agen. Okay. Barium. Barium ion. Okay. So you either change the ending or you don't. And there's a fine line, it is a really nice line, in between the two. Okay. Pretty easy. So tell me, select all of the ones with the correct name. So all you got to do is the first one, potassium. Should I change the ending? No. So it's okay. The second one, fluorine. Should I change the ending? Yeah, so fluorine ion is wrong. It should be fluoride. Okay? Gallium. Should I change the ending? No, so it's the gallium ion. Selenium. Should I change the ending? Yeah, I should. So that would be selenide ion. Okay. And we did magnesium just a second ago, so we know that's got to be right. And S, would you change the ending? So sulfide. Pretty easy. Okay. Then we should be able to go the other way. Right? So, what is the formula for the phosphide ion? Shouldn't have to look through the whole chart because I said "ide," right? And phosp must be phosphorus. Okay? So, it's going to be a capital P. I just have to decide what charge it's going to get. It's going to gain. How many is it going to gain? 3. So when someone says the phosphide ion, P with the 3 negative. Versus phosphate. Phosphate is that polyatomic. So watch those endings. The suffixes tell you something about what you're talking about. If it ends in "ide," you're looking at something off the table. Ends in "ate" or "ite," you know it's polyatomic. If you don't change the name, you know it's positive. Okay. Now, there is a little problem, and that is, what do you do with these? Can I just say the iron ion? Well, if I told you the calcium ion, you can figure out calcium was 2+. If I tell you the iron ion, can you figure out what the charge is? Okay, but it's worse than that. So how can it be worse than that? Not only can't you tell what the charge is, there's more than one possibility. So they have to be specific when they talk about iron. Okay? So they're going to need to use something to tell difference. So that's where I want to stop today. Now, tonight's homework is a reading guide, and I intentionally skipped the first lesson, the first reading from this module. First reading from this module, everything they say in it is true, but I really didn't like the way they explained it. Where I used electron configurations and dots, they used orbital diagrams, which would work too. They're just much harder to draw to get the same idea across. So I skipped all those sections because while it's true, it's not especially helpful. So this is actually going to start halfway down the page in the second lesson where I skipped a whole bunch of stuff. We finally get to some stuff that is meaningful and they did a good job. But our next game is to name these things and write their formulas. Okay? So have a pleasant afternoon. I got to make some water boil. Try it a different way. How many hot plates do I have? How many hot plates do I have? How many hot plates do I have? Let's find out. Yeah. You need to pass for me, yeah. But you want to take your water bottle. Oh, it's not yours? Ah, darn. I was hoping to get rid of it. Okay, you want to pass for tomorrow? I can do that. Hey, you too. And I fixed your stuff, the bell work on my bell work thing. I just didn't get a chance to type them into Canvas. Okay, so I didn't forget you. So you're getting caught up, missing school. Feels so good while you're doing it. While you're doing it, it's not. oh no! There's a hole. Why am I looking up at everything? Right? Yeah, so no matter how bad you think it is, staying home is not any better. Yep. You too. Take care. Sorry. Dangerous place to stand. Well, if I had to open it at some point. They wouldn't let me lock you out. I asked. Do I have to let him back in? Ugh.